We are next going to examine how we can incorporate categorical explanatory variables into a logistic regression model. We have already seen one example of this in the past relative to the place-kicking data example, where we had the change variable. Change was equal to a 1 for a lead change place kick and a 0 for a non-lead change place kick. A key aspect there is that while change had two different levels to it, it was only represented by one variable in our model that was 1 or 0. Whenever you have a variable that is with levels of 1 and 0, that's often referred to as an indicator variable. So change was represented by one indicator variable in the model. Now what happens though if you have a categorical explanatory variable with more than two levels? Or with two or more levels, I should say. And let's say, just to be general, we have a categorical explanatory variable with q levels. Well, to represent that in the model, we would need to have q minus 1 of these indicator variables to represent it uniquely. This corresponds to essentially the same way that you would represent a categorical explanatory variable in a normal linear regression model, if you've seen that before as well. So let's take a look at an example to help explore this further. So suppose we have a categorical explanatory variable with 4 levels to it. These levels are simply going to be denoted by A, B, C, and D. To represent this 4-level categorical explanatory variable in our model, we would need to have 3 indicator variables for it. So here's a table that helps to demonstrate this. The rows represent the 4 different levels. The columns represent the indicator variables that you would use to represent that in the model. So we have a variable called x1, which has a level of 1 for which has a value of 1 for level B of our variable, 0 for all the other levels. X2 here has a value of 1 for level C, 0 otherwise. X3 has a level of 1 for D, has a numerical value of 1 for D, 0 otherwise. Now notice that level A here, if I can circle it correctly, level A here is only going to be equal to 0 throughout for x1, x2, and x3. Now you might be worried, well, are we actually representing A? And the answer is yes. The key aspect here is that notice that each level of our categorical explanatory variable has a unique coding corresponding to these 3 indicator variables. This level A, since it is all zeros there, is often referred to as a base level for a categorical explanatory variable. I could have changed the coding here so that maybe, let's say, B was the base level or C or D was the base level. I chose this particular coding here because this is how R will be doing it. You'll see more about that shortly. So here's our logistic regression model, where I have included this categorical explanatory variable in the model with 3 indicator variables. If one wanted to be a little bit less formal, one could actually write the corresponding levels of the categorical explanatory variable in the model instead, where a value of B represents that I have an indicator variable for B. So it has a value of 1 if we're at level B, 0 otherwise. Now, to help you see that indeed that we are representing all 4 levels of our categorical explanatory variable in our model, let's take a look at what the model would look like for each level. So for A, it's really simple. My model would be logit of pi is equal to beta 0, because x1, x2, and x3 are equal to 0. For level B, I have beta 0 plus beta 1. For, let's say, level C, I have beta 0 plus beta 2. And then for D, I have beta 0 plus beta 3. So the key aspect here is that each level is uniquely represented by a linear combination of these regression parameters. That's why we are actually representing all 4 levels in this particular model. If we look at this a little bit further, compare the model for A to the model for B. Notice the only difference is this beta 1 there. So what beta 1 is actually measuring is essentially the difference between the effect of B and A. Similarly, beta 2 is representing the difference of the effect of level C to A. Sometimes people will have a misconception of like this beta 1 here would be the effect of B compared to all the other levels. But that's incorrect. When we actually compare these two models, it's beta 1 represents a comparison essentially between the effect of B and A. Okay, so let's focus more about how R works with categorical explanatory variables. Well, R has a particular class type for variable called factor that can be used with these categorical explanatory variables. Now, these categorical explanatory variables can have a variety of different names associated with them. And so what R does when it sees it has a factor, it will automatically, inside of R itself, recognize a particular ordering to these to these levels of the categorical explanatory variable. In particular, this is how R chooses the ordering. So you could have a categorical explanatory variable that has some numerical coding to it, maybe like 1, 2, and 3, where it's just a way to represent differences between the different levels. And as you might expect in its ordering, it's going to take 1 before 2, before 3, and so on. But what if these levels are coded in a way that uses letters? Well, A comes before B, comes before C, and so on. But what if you have, let's say, some lowercase and uppercase letters? Well, little a or lowercase a comes before capital A. Also, maybe you have some levels that are coded in a way that some are numbers and some are letters. Well, the numbers always come before letters. Now, this may seem like a lot of specifics here that are not meaningful, but in fact it is. The reason being is because R is automatically going to create our indicator variables for us with respect to a categorical explanatory variable. How it creates the levels depends on this ordering that R chooses. And simply, R uses what's referred to as a set first level equal to 0. Set first level to 0, I should say, ordering. So if we go back to our original example here, notice based upon what I showed you for the ordering, A comes before B, comes before C, comes before D. And so A represents essentially the first level of our categorical explanatory variable. For that reason, this is always going to be then the base level. So that's why it's important to understand how R does the ordering of the levels of a categorical explanatory variable, because it translates into how it forms the indicator variables. Okay. Some other software will actually use a set last level to 0 ordering. So for example, maybe the D level on that exact last example would be the level that has all zeros for x1, x2, and x3. Now, an important thing to consider here is that while you could have different indicator variables represented in a categorical explanatory variable in your model, your conclusions will not change about that corresponding categorical explanatory variable, as long as you understand how these indicator variables are done. So in other words, for example, your estimates for pi will be exactly the same no matter what the ordering is. So the key is to understand is that how indicator variables are formed, or how just in general categorical explanatory variables are represented in the model, is not unique. But you will still get the same conclusion no matter what, as long as you understand what the ordering is about it. From these notes, you'll see ways that you can change the ordering yourself, and I encourage you to try to do that and see that indeed, like your estimates for pi will not change. Okay, so let's look at this example that is in my program for levels.r. So we're going to go back to this categorical explanatory variable that has levels A, B, C, and D in it. Now, to help you understand how R treats it, let's ourselves actually create a factor. Well, I can use the factor function to do that. And the first argument in the factor function is x. And let's say I just put, some data. Maybe, I take a sample and I have a categorical explanatory variable where I observe for the first item a level of D. For the second item, I observe a level of A, and so on. So notice how I put this into the C function here. I put quotes around the corresponding levels. I put that in a variable or an object called cat.var for a categorical variable, and then I print it off. And R recognizes that this is a factor. It's a categorical explanatory variable. It shows you what the data is. So the first value is D, the second value is A, but also notice what it gives you here, levels. Notice the ordering of those particular levels there. Now, most often where we will actually see categorical explanatory variables is in a data frame. So how about we simply put this categorical variable into a data frame and simply give this variable name cat.var in that data frame. I put this into a data frame called set1. I could call it something else. It just seems like that's a simple generic name. And so if I type set1 at my command prompt, we can see that here's my data frame. Now, to verify that indeed that R is treating this as a categorical explanatory variable, what I could do is now use the class function with it. I say class, here's my data frame name, set1. I pull out of the data frame cat.var, and we see that R recognizes it indeed as a factor. I can then also use the function R called levels to see what those levels are. So if I say levels of set1 $cat.var, here is my corresponding levels. And then I can also use a function called contrasts with this variable. And what that does, it shows me how the indicator variables will be formed if I were to include this variable in a regression model. And so notice what R does. It basically forms a table that we saw before. The rows represent the levels of our categorical explanatory variable using the ordering that we see in levels. And then the columns represent what we had for x1, x2, and x3. Now there are cases where you would like to, let's say, reorder the levels. Like maybe, for example, and you'll see as we go along here eventually when we do odds ratios and stuff, we might always want to make a comparison between one level to another across all the different levels of the categorical explanatory variable. For example, maybe I always want to make comparisons to A. So I want to compare B to A, C to A, D to A. Now, or let's actually look at another example. Maybe I want to always compare all the levels to D. So I want to compare A to B, C to B, D to B. How could I do that, let's say in a more simple way to make, in terms of how R creates its output and stuff, what would be a simple way to do that? Well, what one could do is actually reorder the levels so that B would become the base level, for example. Okay, so how can we change the ordering? There is a function R called Relevel that allows you to do that. So I can say Relevel. I take my variable that was in set 1 and I say I want my base level to be D now. I could have chose B. I just chose D in this example here. Ref is just another name for reference, and some people will refer to the base level as the reference level. So that's why that argument name is used. And I'm going to put this into my set1 directly by saying, okay, set1 $cat.var2. And so what that does, it produces a new column in my data frame that looks exactly the same as the previous column, but there is actually a difference. And that is, if I were to look at levels now corresponding to this column, I do see that now D is listed first. If I use my contrast function with this, I can see that D is listed first here, and it is indeed my base level. A more general way to do this is to use the factor function, where now I'm going to put a new variable called cat.var3 in my data frame, and I say factor like I've done before, my x argument. I put my original variable in there, and now I add another argument called levels, where I can actually order the levels here in any way that I want. And so indeed, when we use the levels function with this, we see that we did get the the actual ordering that we wanted. There are ways to rename the levels of a factor as well. Please take a look at my program to see how to do that. Okay, some additional comments. Now, in the place-kicking data set, again, we saw change was represented by an indicator variable that had a value of 1 for lead change place kicks, a 0 for non-lead lead change place kicks. Now, since we have actually created a numerical set of values for this particular variable, I don't need to make it a factor in R. That's fine because we already have the indicator variable, so that's why I didn't do that to begin with. Now, there will be times where a categorical explanatory variable is actually coded numerically. We kind of talked about this a little bit before. Suppose instead of, let's say, using A, B, C, and D as my levels, I could use 1, 2, 3, and 4, where I don't necessarily think of, let's say, 4 being greater than 3 or 3 being greater than 2. It's just a way of coding the different levels. For example, maybe you might be interested in, okay, you take a survey of some people and you ask them, how did they get from their house to the grocery store typically? Do they use level 1, which is by car, level 2, by bus, level 3, they walk, or level 4, they ride a bike? Now, riding a bike is not necessarily greater than riding a car. It's just a coding convention that people are using to designate the different levels. Now, when that happens, if you were to estimate a logistic regression model with, let's say, a variable called x that represents these levels as 1, 2, 3, 4, and if you do not tell R that this is a categorical explanatory variable, R will not form the indicator variables that it needs. Instead, it will just treat this as a regular old numerical variable where a value of 4 is indeed greater than 3, greater than 2, greater than 1. So you need to actually tell R that this is a categorical variable. How can one do that? Well, what one could do is in the actual formula argument itself that you have for GLM, when you enter x in there where you would normally enter in explanatory variables, you could say factor x. In R, then will automatically treat this now as a categorical explanatory variable. Alternatively, in your original data frame itself where you see x, you could say, okay, I'm going to create a new variable in my data set. Let's say the data set again is set1, and I'm going to create a new variable called it, let's say, new.var, and it's going to get factor at x. And R will automatically transform the 1, 2, 3, and 4 to now levels of a categorical explanatory variable. You'll see an example of that coming up. Now do note that there are particular times where R will not go by that ordering that I saw of how the levels are created. And in the end, the reason why R does that is because, without maybe you knowing, you've actually changed the orders yourself. So for example, there is a nice little exercise in my book involving Larry Bird in chapter 2 that shows how we can estimate a logistic regression model to the Larry Bird data set for the free throw shooting that we've seen previously. And in that example, I show how one could take then the contingency table format of our data and almost automatically transform it to a data frame that we would need to use for GLM. Now, in that particular situation, how we've created then the corresponding levels of the contingency table is actually can cause a problem in terms of the ordering of the levels. Now, unfortunately, I didn't include that example here, but let's say I create a contingency table like this. I have counts of 1, 2, 3, 4. And if I create my dimension names, this is the key, where I have the rows in this order, B and A, the columns in this order, success and failure. Notice that this is not alphabetical order here. I'm putting B before A. Well, R, when it automatically does this conversion to a data frame that can be used by GLM, it will treat rows as a categorical explanatory variable where the level B comes first before A. So this is something that occasionally occurs, and I just wanted to mention it. Again, there's an example in my book that helps demonstrate that. Okay, so let's take a look at a nice example that involves two categorical explanatory variables. This example deals with an actual study that was done to look at how one could control the spread of the tomato spotted wilt virus. Simply, it's a virus that can infect tomatoes and make them look not very appealing. Now, to understand this experiment, you have to have a little bit of a general understanding about how viruses are transmitted from one plant to another. So insects will feed on a particular plant, maybe eat the leaves, for example. And let's say if that plant was infected with a virus, that virus then, let's say, can go into the insect. And then when the insect jumps from one plant to the next, because now the virus is inside the insect, it can actually transmit the virus to a new plant. And so that's how the virus can be spread from one plant to the next. And to understand how the tomato spotted wilt virus is spread from one plant to another, some researchers at Kansas State University did an experiment in some greenhouses where they looked at a particular kind of insect called thrips that can spread the virus. Now, to help understand the importance of this problem a little bit more, I have a short video where this was a small segment of the TV show Backyard Farmer, which is produced by the University of Nebraska. And it just so happened in this segment, they talked about tomato spotted wilt virus. So let's go to the video.
And then the last disease we commonly see in tomatoes is a viral disease, and that's tomato spotted wilt virus. Once we get that fruit development setting on, the fruit, instead of being that nice red color that we're after, it's going to be blotchy. We're going to have blotches of red, yellow, and oranges on that fruit. You can still eat the fruit. It's no impact to you, but the virus can move from one tomato to the next and when we have thrips present. So we usually recommend removal of those infected plants and look at thrips using sticky traps to determine if an insecticide application is actually necessary to control the insects in your garden.
Okay, so we can actually see there the results of these thrips spreading the virus from a tomato plant to another tomato. You know, these tomatoes don't look very appealing anymore. And so what these researchers at Kansas State University did was they had a greenhouse, where they had multiple greenhouses, I should say. In each greenhouse, they put 100 uninfected tomato plants. And what they wanted to do was introduce the virus to the greenhouses in one of two different ways. So this is our first categorical explanatory variable. It has two levels to it. They refer to this as the infestation method. The first way was to intersperse additional infected plants among the good ones or the unaffected ones, and then release uninfected thrips to spread the virus. With the idea again is that these uninfected thrips would eventually get to these infected additional plants, feed on it, and then potentially start spreading it to the uninfected plants. The second way is releasing the thrips, releasing thrips in a greenhouse that where these thrips already carry the virus. So one of two infestation methods are applied to each greenhouse. The variable in our data set that we're going to be looking at corresponding to this is called infest. It has a level of 1 and a level of 2. Notice this is a categorical explanatory variable that is coded numerically. Now the second variable of interest was ways to control the spread of the virus in the greenhouses. They looked at 3 different ways: a biological control where predatory spider mites were released into the greenhouse as well, a chemical control, meaning that they apply a pesticide, and then they also want to say, look at, well, what happens if they didn't do anything at all? So no control. So our second categorical explanatory variable is called control. It has levels of B, C, and N. So my corresponding data is in the data file tomato virus. And so I can read the data into R just like what we've done in the past. But there's one key difference that's very, very important. I include an argument called strings as factors and with a value of true. The default is false. With a value of true, what R is going to do is that whenever it sees a particular variable that has character values in it, it will treat that variable as a factor. So it automatically creates this factor for us. So that's great. This actually used to be the default behavior of R until a few years ago. And so if we take a look at the data, so the first 6 observations by using the head function, what we see is that in the first greenhouse, infestation method 1 was used, a chemical control was used. There were, of course, 100 plants, and 21 of these plants, after 8 weeks, had the virus. The second greenhouse, infestation method 2 was used. A chemical control was used again. 100 plants. 10 of those plants came down with the virus. So what we see here is that we have a binomial format to our data, where in this case, coming down with the virus is actually a success. So 21 successes for the first greenhouse, 10 successes for the second greenhouse. Okay, so that's what the data looks like. Next, what we like to be able to do is explore this data a little bit further to make sure that we understand how the categorical explanatory variables are actually being represented. So to do that, I can come over here to 10. Again, read in my data. And I can say, let's look at the class for the control variable in tomato. Notice it says factor. That's good. Let's take a look at the levels. Okay, it has levels of B, C, and N. Notice the ordering there corresponding to what we talked about a little bit earlier. And with the contrast function, then we can see how this particular explanatory variable will be represented in a logistic regression model. We can see that there will be 2 indicator variables representing the 3 levels of this categorical explanatory variable, where B is the base level. Now let's take a look at the infest variable. Remember, this has levels of 1 and 2. Oh, R treats this as integer. Well, yeah, those are integers in there. You know, we see values of 1 and 2. But we want R to treat this as a categorical explanatory variable. So we need to tell R that indeed this is what we want. And if we actually were to, let's say, use levels with it, we had null. So what I'm going to do is use the factor function in much the same way as what we did before. Where inside the factor function, if I wanted to, I could put x equal tomato $infest. And since we want to always treat this variable as categorical in nature, how about we just replace infest that's in tomato already with this new version of that variable. So let me go ahead and do that, and then we'll look at the first 6 observations. The first six observations don't change, but now the way that R recognizes infest is actually as a factor. So I can just run the class levels and contrast functions with that just to confirm that indeed that is true. Okay, let me come back over here to my Word document. Now, in the end, since infest only had 2 levels to it, and it was coded numerically to begin with, I could have just left infest as is. As long as I recognize that, let's say, 2 is not necessarily greater than 1, I could have left it as is, and I could have proceeded with my analysis. Much the same way with the changed variable in the place-kicking data set, where it had numerical values of 1 and 0. Now you might be wondering, well, wait a second, 2 and 1 is not an indicator variable. That is true. There are multiple ways that you can code this stuff, as long as you understand that what 2 and 1 is. When you actually interpret your corresponding model, everything's fine. You're still going to come up with the same estimated probabilities of success. If there are still some doubts, I recommend actually trying it on your own to see what would happen. Okay. Now let's go ahead and estimate then this logistic regression model. So to do this, I'm going to create an object called mod.fit. That's where I'm going to put the results in. I use the GLM function. I use my formula argument. A key here is that this is, again, binomial response format data. So virus 8 is my count of successes / plants, the number of trials. Tilde, I want to include the infest variable and the control variable in my model. R automatically will produce the indicator variables for us. Family argument as before, data argument tomato, and don't forget this is maybe the number one place that sometimes my students forget to include in this kind of a model where I have a binomial response data format. Weights equal plants. That tells R what the number of trials are. And so if I go ahead and run this code and I summarize the model's fit, excuse me, this is what I get. Let me come back over here to Word so we can look at it more closely. And so what we see here for our estimate column, we have our corresponding beta hats as before. Notice how the rows are labeled here. Since infest is recognized as a categorical explanatory variable, using the set first level to 0 formulation, R creates an indicator variable for level 2 of infest. So infest 2 is an indicator variable that has a value of 1 when it's infest level of 2, a value of 0 otherwise. Take a look at the control variable. Again, how R approaches this, it has levels of B, C, and N. So level C is going to correspond to an indicator variable, the first indicator variable. It has a value of 1 for level C, a 0 for levels of N or B or otherwise. Same thing happens with level N. Okay, so with that output then we can go ahead and state what our estimated logistic regression model is. Notice how I actually write this out. Infest method 2, control C, control N. These are recognized as indicator variables. If one wanted to, one could simply just write C and N for control here. So you would just have C, you would just have N. It's up to you. Obviously, we don't want to just put 2 there because that would be quite confusing with these numbers listed there. Now, some interesting things to see with this estimated model, and again, this is now just for the sample itself, what I'm going to be talking about, is that notice here that we have a positive 0.2196. So what that says is that the estimated probability of success is higher when using infestation method 2 than using method 1. This is just for the sample. I'm not making conclusions about, let's say, an entire population. Take a look at this. Control N has a positive estimated regression parameter in front of it. So what that says is that the estimated probability of success of coming down with the virus is higher when you use no control method versus you use control method B. Remember, that's the base level. Using control method C, notice I have a negative there. So this model is estimating that using a chemical control reduces the probability of these plants becoming infected when compared to level B of control. Okay. We will more closely or more carefully interpret these corresponding explanatory variables coming up. We'll use odds ratios to do this. Also, I don't want to interpret them too much yet because it actually would be best to include an interaction term between these two categorical explanatory variables before we interpret it fully. And so we will do that a little bit later on too. Okay. What about doing hypothesis tests involving categorical explanatory variables? So if we go back to our previous example where we had a 4-level categorical explanatory variable with levels of A, B, C, and D, again we represented that variable in our model with 3 indicator variables. Now to test the importance of that categorical explanatory variables, we cannot necessarily just look at, let's say, one of the betas. We have to look at all 3 betas that correspond to x1, x2, and x3 in the model to do an overall test for that categorical explanatory variable. So it would take all 3 of these betas to be 0 for that categorical explanatory variable to disappear in the model. So I would need to do this particular hypothesis test. What you will see in the output that unfortunately R automatically gives you with the summary output, it does the Wald test for each individual beta. Just ignore that. It's not very meaningful. What we need to do is one overall Likert ratio test for this hypothesis to judge the importance of that particular variable in the model. Well, what about how do you include interactions in a model? To form an interaction, when we did, let's say, with the place kicking data before, we had this particular model, beta 0 plus beta 1 times the distance plus beta 2 times wind. And then to form the interaction, we did beta 3 times distance times wind. So to form what's referred to as a two-way interaction between 2 variables, we just simply multiply those variables together in our model. What happens if we have categorical explanatory variables? Well, you do the same thing with each of the indicator variables now. So you take each of the indicator variables times all the other corresponding terms for the other explanatory variable of interest. So for example, let me take my model here. Let's relate this to the model that has a 4-level categorical explanatory variable. Let's say I have another variable in my model that's maybe a continuous variable, and it's called, let's say, V, for the lack of a better letter. If I want to find then the interaction between the categorical explanatory variable and V, what I would need to do is add to this beta 5 times x1 times V plus beta 6 times x2 times V plus beta 7 times x3 times V. That's what I would need to do. How would I evaluate then the importance of this categorical, how would I evaluate the importance of this interaction in the model? Well, I would need to do a hypothesis test corresponding to each of those betas that were added for that interaction term. So that would be my null hypothesis there. Alternative is at least one of the betas does not equal 0. Well, what if though I had an interaction between a categorical explanatory variable with 4 levels and another categorical variable with explanatory variable with 3 levels? So that means I'm going to have 3 indicator variables there. I'm going to have 2 indicator variables there. What would I need to do? Simply take the product of all the corresponding indicator variables here with all the ones there. Okay. So let's take a look at an example. This is going back to the tomato spotted wilt virus example. If I want to include an interaction in this model between infest and control, I include it in a similar way to what we've seen before. R automatically finds the products of the indicator variables that we need for the interaction. So if I estimate the model and I summarize the model, here's the 2 additional rows that we have corresponding to now our beta hats for these interaction terms. So infest had 1 indicator variable, control had 2 indicator variables. So that means I need to take infest2 times control C, infest2 times control N. And so now I can state then my estimated logistic regression model. Here are the additional terms corresponding to the interaction. If I want to then do a Likert ratio test to determine if in terms of the population model, is this interaction important or not? In other words, I want to do a test of beta 4 and beta 5. Are they together equal to 0, or is at least one of them not equal to 0? To do that test, I can do a Likert ratio test. We have seen a variety of different ways to do these Likert ratio tests in the past, and this time I'm going to use the capital ANOVA function from the car package to do that. And so here are my results. If I look at the interaction row, so notice how R is actually writing this, because we have an infest control interaction. It doesn't write out all the indicator variables involving it, but notice there are 2 degrees of freedom. The reason being because there's 2 betas that are being tested there. My -2 log lambda statistic is 28.224. Using a chi-square 2 approximation, one can then find out the p-value. The p-value will be the probability of A being greater than 28.224, where A has a chi-square distribution with 2 degrees of freedom. That p-value is 7.4 times 10 to the -7th power. So there is sufficient evidence to indicate that indeed, yes, that interaction is important in our model. So some things for you to think about on your own. Make sure you could use the little ANOVA function to perform this test as well. To do this, what you'll need to do is take the estimate of the model without the interaction term and the estimate of the model with the interaction term, put the corresponding mod.fit objects inside of ANOVA to do the test. Also think about, well, what do the hypotheses for the p-value of infest here or control here, what do those corresponding hypotheses test? We talked about this a little bit before with respect to the distance and wind example. If you're not for sure exactly what the answer is to this question, go back to that example and you'll find out how to address that question. Okay, so that then concludes this subsection on including categorical explanatory variables in the model in terms of how to estimate the model. A later subsection will look at more thoroughly how to interpret these variables.